bounce here. Let's take a class in Fourier transforms. So Fourier transforms is a mathematical tool that is used to decompose a function, okay, often a signal, to decompose the signal into its various frequencies. So decompose, a mathematical tool that is used to decompose a signal into its frequency components. All right, into its frequency, okay, components. Okay, all right, and then also it is used to transform the signal, okay, transform the signal, okay, from time domain into frequency domain. Okay, so just as Fourier series is used for periodic signals, Fourier transforms are used for aperiodic signals. Okay, so now let's see how we can be able to derive a formula for Fourier transform, okay, from the basics of Fourier series. Okay, so deriving Fourier transform. Fourier transform, okay, deriving, please, Fourier transform from Fourier series. Okay, so deriving Fourier transform from Fourier series. All right, so we are aware that Fourier transforms, from the previous examples that we have done so far, if you followed, you realize that we used to write signals like this. Okay, signals of this sort. Okay, we used to write signals of this sort. Let's say here is 0. Let's say T. Let's say T. Okay, and then from this signal we will be able to realize its from this signal we could realize its frequency spectrum or magnitude spectrum. Okay, magnitude spectrum. With magnitude spectrum here becomes what? The W, frequency, against what? Amplitude. Okay, against amplitude. Let's say Cm. Okay, some people may use other variables like Cn. Okay, so let's say this one here is 0. Let's say this one is like this. Let's say this one is like this. Let's say this one is like this. Let's say this one is what? Like this. Okay, so yes, say here is 1, here is 2. Let's say this one is like this. So here is 3. Let's say this one is like this. So here is 1, minus 1, minus 2, and minus what? 3. So this is the what? Frequency spectrum of the x of t of the periodic signal here. Okay, of the periodic signal. Okay, so this one is the frequency spectrum. But this frequency spectrum, you see that they are occurring at what? Instances of time. They are occurring at instances of time. So here, because it's occurring at instances of time, this I can call this W, which in the normal magnitude spectrum or frequency spectrum, which is called W, because it is occurring at specific instances of time, I can call it what? N, meaning number of what? Samples. Okay, I can call it what? N, meaning samples. Okay, and here, because it's occurring at this instances of time, discrete instances of time, specific instances of time, I can call it discrete. I can call it discrete discrete magnitude spectrum. Okay, so I can call it what? Discrete magnitude what? Spectrum. Okay, discrete magnitude spectrum. All right, so here basically here is how it can be done. Okay, so let's imagine that this discrete magnitude spectrum or discrete frequency spectrum, which are occurring at instances of time. Let's imagine the case whereby they are squeezed together. These points that are occurring at specific instances of time, if they are squeezed together, then that means that they will become so compact that they will no more continue to be discrete, but it will become very close. If they are pushed together, okay, if they are pushed together, it will become so close that they will behave almost as continuous time. Because if you push them together, they will become close, and they will not be no more wide apart with specific spaces between them. But now they become so close as being continuous in time. In that case, they can be represented in this particular format. Okay, in this particular format as x of t. Okay, in that case, it will come back to x of t. So here becomes like t. Okay, and then here, if you want to be able to get this one, the spectrum for this one, then you're going to have something like this. Okay, you're going to have something of this sort. Okay, for the spectrum for this signal. Okay, all right. So now here, this spectrum here is is no more discrete spectrum, but this one is continuous spectrum. Okay, continuous spectrum. And here is omega. Okay, and here is omega. And then here is x omega. Okay, so now let us move on from here. Okay, so now we are aware that x of t. Okay, this x of t, xt of t, in the normal Fourier series, we were having we were having summation from infinity up to infinity from minus infinity is cm. Okay, cm into e j n. Okay, omega naught t. Okay, this is what we were having. Okay, and we were having that cm is equals to 1 over t into t naught into t naught plus t. Okay, into xt of t. Okay, xt of t into e minus jn omega naught t dt. Okay, we were having this. All right, this is what we were having. All right. Okay, so now what we can see now, what we can do with this one is that we can give some period. Okay, we can give some period to the signals. So let's say that this place is what? Let's say that this place is minus t on 2, and then here is t on 2. Okay, so if I put there to minus t on 2 and then t on 2, then I'm going to have cm is equals to 1 over t into t naught into t naught plus t. Okay, into t naught plus t, and then I'm going to have here xt of t into e minus jn omega naught t dt. Okay, so I'm going to have this one. Okay, but because I have put here to be minus t over t and then t over t here, please let me introduce that limit into my equation. So 1 over t here. Okay, I'm going to have 1 over t here, and here I'm going to have minus t on 2, and then here t on 2. okay, and then I'm going to have xt of what? T into e minus j n omega naught what? T dt. Okay, so this is what I'm going to have. Okay, so this one I'm going to have. So now let's say that in the case whereby I bring this t here, then I'm going to have t into what? Cm into which is equals to what? T on what? 2 minus t on what? 2. Okay, minus t on 2. Okay, which is going to be equals to xt of t into e minus j n omega naught what? T. Okay, which is equals to this one. Okay, so now let's see in the case whereby we have these particular instances. Okay, whereby we have these particular instances. Okay, so if t is approaching infinity, then what it means is that this my xt of t will also be approaching what? X of t. Okay, it will be approaching its original continuous time form. Okay, and in that case, the discrete, okay, then my discrete distance will now become what? N omega naught, meaning that now they are being what? Squeezed together. So n omega naught, okay, n omega naught, okay, is being squeezed together. So now if this one is being squeezed together, then it is becoming what? Omega. Okay, so now it will be approaching what? Omega. Okay, so now if this one is approaching omega, then from what I just wrote, okay, what I can deduce from that is that this tcm, okay, tcm, okay, is going to be what? Equals to what? X what? Of omega. Okay, it's going to be what? X of omega, where x of omega, okay, where x of omega is equals to from infinity minus infinity, okay, into x of what? T, because I told you that this x of t here is approaching what? X of t. So here becomes what? X of t into e minus j n omega naught what? T dt. Okay, so this is what I am going to get. But I have also told you that n omega naught is approaching what? Omega. So that means that n omega naught will also get away. Okay, so now my x of omega is actually going to be equals to what? From infinity minus infinity, x of t into e minus j omega what? T dt. Okay, so this is what I will arrive at. Okay, this is what I will arrive at, and this is called, okay, this formula is called, okay, this, okay, is called Fourier. This is the Fourier what? Transform. So this is the formula for what? Fourier transform. Okay, so this is the formula for Fourier transform. All right, so now this is the formula for Fourier transform. Okay, so now here what we have is that x of t will give you what? Fourier what? Transform, which is x of what? W. So this is the formula for Fourier transform. So from here we can develop the formula further, okay, to also achieve what is called the inverse Fourier what? Transform. Okay, the inverse Fourier transform. So let's look at that one also very briefly. Okay, so here I have that xt of t is equals to summation from infinity minus what? Infinity. Okay, n is equals to, okay, minus infinity Cm into E J n omega naught what? T. Okay, all right. So here, what we can deduce from here, from our previous formula, is that TCm, okay, TCm is equals to what? X of what? Omega. Okay, X of omega. Okay, so now here, what we can say is that Cm is equals to what? X of what? Omega over what? T. Okay, X of omega over T. Okay, and then so from that, if we have that, then what we can say is that X T of T is equals to summation up to infinity from negative infinity. Okay, Cm, what is Cm? X of what? Omega over what? T. X of omega over T into what? E J n omega naught what? T. Okay, E J n omega naught T. Okay, so now we also know that T is equals to what? 2 pi on what? Omega naught. Okay, so here I can therefore write that xt of t is equals to, here I'll put 2 pi, this one over there. Okay, so here is summation up to what? Infinity. N is from what? Negative what? Infinity. Over what? Over, please let me write this section again. Okay. Okay, so what I'm saying is that I can write xt of t, okay, to be equals to what? This one. N is equals to minus what? Infinity. Okay, so here I can have x of omega, okay, over what? 2 pi on omega what? Naught. Okay, 2 pi on omega naught into E J n omega naught what? T. Okay, so here I can make that formula x of t to be equals to summation up to infinity. N is from negative what? Infinity. Okay, I can have it as, if I reciprocate this one, then it's going to be x of what? Omega over what? Over 2 pi into E J n omega naught what? T. Okay, into what? Omega naught. Okay, into omega naught. All right, so now let's say that in the condition whereby t is approaching what? Infinity. Okay, and then t is approaching infinity. If t is approaching infinity, then n omega naught is going to approach what? Omega. Okay, and then omega naught, okay, is going to be what? Is going to approach what? The omega. Okay, because we know that, because why? This one, okay, since what? Since omega naught is equals to what? 2 pi on what? On t. So now as t is approaching infinity, omega naught will be approaching what? The omega from here. Okay, we'll be approaching the omega from here. So now, all right, let's get another sheet. Okay, so here what we're now going to have is that if we have that condition, then our summation, which is this one, is now going to turn into what? Integration. Okay, it's now going to turn into integration. So now, if it's going to turn into integration, then I'm going to have what? X of what? T is equals to what? Because I have told you that this x of t is approaching what? X of t. Okay, so it's going to be like this one. So here it's going to be 1 over what? 2 pi into what? Into infinity minus what? Infinity. Into what? X of what? Omega. Okay, into E J omega okay, d what? D omega. Okay, so we're going to have what? This formula. And this formula is called what? The inverse Fourier series what? Formula. Okay, the inverse what? Fourier series formula. So this one is what? Inverse Fourier series. Okay. All right. So that is the end of it. Okay. So these two formulas are very important. This formula, which is the what? Fourier transform formula, and this one, which is the what? Inverse Fourier transform. Okay. Sorry, it's not inverse Fourier series. Okay. It's the what? Inverse Fourier transform. All right. Sorry. So inverse Fourier what? Transform. All right. So this will be the end of this lecture. See you in the next one, in the next lecture. Thank you.